Hi, thanks for joining us today. Today we're going to be talking about lesson 6-6, which is the last lesson in this unit. We're going to be talking about volumes of revolution. So, this is extending the ideas that started in 6-4 and continued into 6-5. If you haven't mastered those videos yet, if you haven't done those homeworks yet, this will be hard. Please make sure you have a firm grasp on 6-5 and 6-4 before watching this video. Here we go. If, for a given base, you had a semicircular cross-section sticking both toward you and away from you, you would have a circular cross-section. So, for the circular cross-section, the area would be pi r squared, which would be pi r squared dx for perpendicular to the x-axis, pi r squared dy perpendicular to the y. Again, this is based on the idea that the volume equals an integral of an area times a dx, an area times a width. So we're talking about more or less, and this is where it gets hard to draw, but if I had, draw it this way, a region sticking into the plane, and I was going to put some circles on that region, again where that's the maybe diameter, a bunch of pokeballs, I don't know, dipping both over and under. It's hard to visualize, but what you would have instead of the kinds of shape we were talking about last chapter, last section, we would have something more of a regular cone, not just a half cone. Okay? That's the idea. Talking about solid circles all throughout here. Let's see how this would work. So, using the region bounded by here, by y equals x squared, this upper parabola, and y equals negative x squared, the lower parabola, the downward facing parabola. We're going to start from x equals 1, x equals 0, stopping at x equals 1. We have this shaded area, and we're going to stick circular cross-sections onto those slices. So again, picture that paint coming out of the page and into the page, out of the screen and into the screen, toward you and away from you. Okay? So, we have a vertical slice. We're talking about volume equals an integral from a to b, the area of those cross sections times dx. Go ahead, you can try this out. Make sure you're careful about what this slice represents. I'm going to start in 3, 2, 1. So clearly our slice needs to move from the left to the right. That's still part from 6-4, 6-5. We're still going to start at 0 and stop at 1. Like the prelude said, we're using pi r squared. So the real question becomes, what is the radius of a circle like this? Well, the radius, you could do one way or the other. So this is a diameter. That would be the diameter. That would be the diameter of the circle. So extending the idea from 6-5 rather, we'll move the pi outside. We'll do the top side, x squared, minus the bottom side, careful with your parentheses, and we'll divide all of that by 2 since that represented the diameter, and we want to get the radius squared. So let's simplify. Pi integral. That would be 2x squared plus x squared. And if we divide 2 by 2, we get 1. One of the hardest things to do in math right there. Square, square. That's right, though. So, instead of thinking of this as having one diameter that we're splitting in half, we could have also arrived at the same conclusion by picturing revolving this piece, because that was exactly a radius. And that would have just been the distance from x squared to the axis. That's our major idea today. So, what am I talking about? I'm saying we would have gotten the same shape by looking at the square function, x squared, taking a representative rectangle and revolving that rectangle around the x-axis, making a disc type shape. And that's the key to what we'll call the disc method or the disc formula. So the top paragraph is summarizing what I just said. Circular cross-sections can also be formed by revolving very thin rectangles about an axis of revolution. So in the example we just did, I would call that x-axis the axis of revolution. We would make a disc like a CD, like a, thin circle. These circular, a volume formed by revolving a region about a line is called a solid of revolution. That line is called the axis of revolution. This is just terminology. We'll mention, here's something that's important that usually comes up. The line that does not pass through the interior of the region, okay? We'll never be dealing with, if you've drawn your line, if you feel like the axis of revolution passes through the region, you've done something wrong. If a region is bounded by the axis of revolution, the volume of the solid of revolution is a sum of the volumes of essentially an infinite number of disks. So again, this is treating everything we've done as adding up, and again, that would be basically an area. The pi r squared would be the areas times a width. And that's how we're getting disks. Rather than focusing on that so much, again, we're just going to be picturing revolving. So one more time, we're talking about, here's my picture. Let's revolve this little rectangle here around the x-axis. And we're getting a perfect circular cross-section by revolving that rectangle. So same idea, same formula, different idea. Same idea, different formula. However you want to leave it. So that's what we would get by revolving this whole region. And I often say revolving the region. Doesn't matter. We're going to revolve a representative slice in that region. So that guy represents R. So what are we going to do? We're going to have volume equals pi times the integral. Where do we want to start adding these rectangles? Well, it's a dx rectangle. So we're going to start adding these rectangles up from the leftmost x bound to the rightmost x bound, the lowest x value to the highest x value. And my radius here would be given by the top, this parabola, minus the bottom, and don't forget to square it. That second squared here is the easiest thing to forget. It's pi r squared. You're dealing with a lot of easy issues that people will get confused with. There's a lot of places squares can go. That's one of the main things in this lesson. Just be careful. That's it. We set it up. That's all it needs. You should notice if I wrote it a little differently, we would have x squared squared, which is what we got from the warm-up example. So it is doing the same exact thing, just perhaps a little more clearly. That's why usually you won't see problems asking for circular cross-sections. They would instead just say volume of a solid of revolution, a solid formed by revolving. Okay? That's all it means. We're revolving those disks, getting a nice wheel, a nice disc shape. Next. Now this one asks me to find the volume, formed by revolving the region in quadrant 1, bounded by, and again, bounded by is a cue for you. Bounded by should mean you're going to sketch it or think about how this region looks. Y equals x squared. We just dealt with that. Not so curvy of a parabola, I know. Oh well, just sketch. X equals 0, y-axis. Y equals 4, that's a horizontal line. And we're revolving about the y-axis. So when we're talking about a volume of revolution, I'm usually going to make that notation to know where I'm revolving around. I'm so sorry. So here it was over the x-axis. Now, you might be saying, hey, our axis of revolution is going through the region. Careful, careful, careful. Our region is only in quadrant 1. That's all they asked us to find. So this region in quadrant 1 is only over here, everybody. Careful. Color, color, color. Okay. So, if we're going to be revolving around the y-axis, I keep doing that, I'm so sorry. Revolving around the y-axis, that means I want to be perpendicular to the y-axis. Right? If I'm going to revolve around here, I need somebody sticking out like that. So that means we're talking about dy. And when you saw dy, hopefully your brain said, oh, I got to solve for x. So all that has to trigger that. About the y-axis means we got to be perpendicular to the axis revolution here. We're going to have a slogan for that. Once I knew it was perpendicular, I knew it was a dy. Once I saw dy, I know I need to solve everything for x. All right. Well, who needs to be solved for x? This guy. X equals plus or minus the square root of y. So we're talking about x equals positive root y, negative root y. 6, 5, the very last example, talked about how you could identify which part of this parabola is positive root y, which part's negative root y. Positive root y will give us the positive x values. So that guy is x equals positive root y. That one's x equals negative root y. So this is important because we're not going to really be thinking about that. That's not really a bound of the region we're talking about. Okay, so when we're doing left minus right now, our slice goes through the whole region, but it's important that our region stops in quadrant 1. I hope that is clear. Please rewind the video if that did not make sense. Pi, sum integral, dy, because our slice was perpendicular to the y-axis. So our bounds, because we're doing y bounds, because it's a dy integral, will have to be the lowest y value to the highest y value. The lowest y value is 0. The highest y value is 4. You can picture this slice moving from the bottom to the top of this region. And now we're going to do right minus left here, everybody. Right? That's my radius right there. Right minus left. The right side is definitely root y. The left side is that 0. And we're squaring that whole region. Now, fight the urge to be done there. There's a lot of work, but it asks us to find the volume. So I'm actually going to go through and simplify. Not much to simplify there. Don't drop the pi. It's really easy to drop the pi between steps. Root y minus 0 is just root y. And if I square that, I just get y. The integral of y dy should be pi times y squared over 2. 4 squared over 2 minus parentheses pi times 0 squared over 2. That's an acceptable final answer. I'll box it just so you're all clear. You could stop right there. Careful that my y doesn't look like a 4. I'm sorry, the vice versa. That should be a 4, not a y. If you did simplify, 4 squared is 16, 8 pi. So this region, this volume that you would get by revolving these slices from here to here would be 8 pi. That's enough for now. I would say you could go ahead and do problems 1 and 2. It's only 1A and 2A. Okay? Just to get your feet wet. I don't want this video to turn on to too long. From page 129. Okay? 1A and 2A. I'm going to cut the video off here. If you have the tolerance, go watch the second part, and you can do a lot more of these problems. Goodbye for now. Good luck on those problems. Have a nice day.